Hi, my name is Harrison Platt, and for my project, I investigated the ideal launch angle and exit velocity for different metrics in baseball using StatCast from a specific month. So I created a model that took various tries in order to fit for it to be statistically significant with respect to r squared, but I finally found one. So I had to convert to meters per second for the launch speed and then convert the launch angle to radians. As you can see, r squared is fairly high, making it statistically significant. Basically, within the model, I used hit distance and launch speed with relation, or launch speed and launch angle with relation to hit distance to see if there was a correlation, which there obviously is. So I created a Shiny application, and I created a simulation of 10,000 hits, allowing the user to decide what the launch angle and launch speed they wanted to see. So basically, there's a slider, as I'll show you in a second, that you can decide between different angles and different launch speeds and exit velocities to see how far the ball will travel according to simulation. I also added the distance to center field for each stadium so we can see which hits are homers in which stadiums, which is a really cool part of it. I did that by using basically I just went on Wikipedia and found the distance to center field for each stadium and then added it into the function. The model's pretty cool because it also highlights in red which is a home run. So let me show you exactly how that works. Just run this code quickly. So as you can see, there's two slider options here. There's the speed in miles per hour and the angle in degrees. So let's go, we can pick whatever stadium. Let's go with the Blue Jays. Let's see, at 66, it also gives you the distance to center field here. So let's see. At, for example, a launch speed of 120 miles an hour and let's see, probably around 30. And around 30, almost everything is a home run there. You could also slide it all the way this way at a launch degree of 5 degrees, which is obviously never going to be a home run. And you can do that for all the different stadiums I have here with the distance to center field. So that's my Shiny app. I also created code for the optimal combo according to my model. I created a matrix to see what the optimal combo of the launch speed and launch angle was according to the model, and as a result, I got an exit velocity of 120 miles per hour and launch angle of 45 degrees. So according to my model, 100% of the hits in the simulation at this combo are home runs, and that home run is marked by 300 feet in my model. I made the model so home run is 300 feet. I just decided that that would be the kind of universal distance for the home run, just for the ease of the code in the model. So this is a histogram. The histogram doesn't actually display the optimal combo. The code here displays the optimal combo with 120 and 45. And as you can see, I created code that gives you the mean distance. So for this model, the histogram on the right shows a combo of 120 miles per hour and an exit velocity launch angle of 10. So it basically gives you the distance. And at that 300 feet marker, as you can see, that's the frequency of homers hit. And then this part right here, the bottom code, shows you that 100%, as I mentioned on the slide before, at the angle or at the speed of 120 and an angle of 45 are home runs deemed by that one down there. So if you were to change that around in the code, obviously it'll give you a different percentage. displaying what percentage of those are home runs according to the model. Like I said, the 300 is the marker of how far the distance is, or is the marker of what I deem a home run in this model. So I also wanted to look into the optimal launch angle and exit velocity for batting average. So I created another model visualizing estimated batting average as a function of launch angle and exit velocity. So as you can see, the darker means lower batting average of the little circles in there, and then the higher means the lighter means higher batting average. So as you can see, line drives have a very high probability of being a hit, which makes sense because they're hit faster and they're harder to field. There also appears to be a sweet spot in the model where almost all batted balls are hits around the launch angle of 25 degrees and at least 80 miles per hour in exit velocity. So as you can see, there's a little white gap between the ground balls and line drives, and that white gap is almost 100% batting average. So I guess in terms of the ideal combination for high batting average, you want to be hitting somewhere between 90 and 100 in exit velocity, and somewhere between, I'd say, 15 and 25 degrees in launch angle, and that should most likely result in a hit. And then lastly, I created a model showing the optimal launch speed and angle for distance. In this model, it shows that there's a sweet spot around 80 miles an hour to 100 in exit velocity, and between 25 and 35 degrees for launch angle. So the darker here is a smaller distance at 0, and then the lighter blue is a higher distance around 500. So like I said, I guess for the optimal distance, you want to be hitting somewhere between, again, that 80 to 100 mile an hour exit velocity, and then 25 to 35 degrees for launch angle. And yeah, thank you.